AQA GCSE Chemistry, moles, reacting mass and equations. Starting with a review of how to calculate numbers of moles from mass and vice versa, the reacting mole ratio, reacting mass calculations, and then using moles to balance equations. The essential formula is the mass of 1 mole of a substance is the relative formula mass in grams. So that means the numbers of moles is equal to the mass of that substance divided by the relative formula mass in grams. Now, you may have been taught to use the term molar mass, but it does not appear in the AQA specification. So I'm going to stick with relative formula mass, and that will always be in grams. So calculate the numbers of moles in 48 grams of magnesium. I'll just demo this. 48 divided by 24. Where did I get 24 from? It's the relative atomic mass of magnesium appearing in the periodic table. So its formula mass is 24. So mass of substance divided by relative formula mass, 48 divided by 24 is 2 moles. Stop the lesson. Calculate the numbers of moles in 1.2 grams of magnesium. Okay, so I'm going to reveal 1.2 divided by 24, 0.05 moles. 2 new problems. Calculate the numbers of moles in 22 grams and 1.1 grams of carbon dioxide. Stop the lesson, come back to check and correct when you are ready. Okay, so mass of substance, 22 grams. The formula mass of carbon dioxide, we're no longer dealing with atoms, we're into a molecule or a compound, so 12 for carbon and 2 oxygens. 12 plus 2 times 16 comes to 44. So 22 divided by 44 is 0.5. Similarly, 1.1 grams divided by 44 comes to 0.025. Notice I've dropped putting the units of mass into the calculation. That is normal practice in chemistry. We'll just do 22 divided by 44, 0.5 moles, for example. So we need to calculate the numbers of moles from a mass of substance, because in experiments, of course, we're not measuring numbers of moles directly. We're going via a quantity such as mass. So we need to be able to convert the mass of substance into numbers of moles, and we're going to divide by the relative formula mass. So mass divided by relative formula mass gives us numbers of moles. Now, a simple rearrangement will give us the mass of substance being the numbers of moles times the relative formula mass. So rearranging, bringing relative formula mass up to on the left-hand side and just reversing the order. So mass of substance is numbers of moles times relative molecular mass comes up here, relative formula mass. Calculate the mass of 0.3 moles of magnesium. Well, 0.3 times 24. 24 is the formula mass for magnesium. So 0.3 is the numbers of moles. So numbers of moles times relative formula mass, 0.3 times 24 comes to 7.2 grams. Stop the lesson, calculate the mass of 0.005 moles magnesium. Okay, so multiply 0.005 by 24 comes to 0.12 grams. 2 more problems. Calculate the mass of 2 moles and 0.025 moles of carbon dioxide. Stop the lesson, check and correct when you are ready. Okay, so 2 times 44, if you remember carbon 12, oxygen 16 twice comes to 44. 12 plus 32 comes to 44. 2 times 44, numbers of moles is 2. 2 times 44 comes to 88 grams, the mass of 2 moles of carbon dioxide. I hope you carried this out. 0.025 is the numbers of moles. Again, times 44 comes to 1.1 grams. So let's move on to the reacting mole ratio. This has a jargon name, stoichiometry, but AQA spec just refers to reacting mole ratios. Reacting mole ratio. It's the ratio in moles of each substance reacting and being formed in a reaction. And of course, this ratio is included in balanced chemical reaction equations. So, for instance, typical equation, 2Mg plus O2 goes to 2 MgO2 magnesium oxides. This equation tells us that 2 moles of magnesium reacts with 1 mole of oxygen, O2, to form 2 moles of magnesium oxide. So this is our reacting mole ratio, 2 to 1 to 2. And it's fixed regardless of the starting amounts involved. So you need to be able to use the reacting mole ratio to predict moles of product or moles of reactant. So starting with the equation we had on the last slide, 2 moles of magnesium reacts with 1 mole of oxygen O2 to form 2 moles of magnesium oxide. Predict how many moles of magnesium oxide will be formed from. So I'm going to model the first one, 4 moles of magnesium. How many moles of magnesium oxide from 4 moles of magnesium? Well, if 2 moles of magnesium makes 2 moles of magnesium oxide, then that is a fixed ratio. So 4 moles of magnesium would form 4 moles of magnesium oxide. Stop the lesson and predict the moles of magnesium oxide from these starting quantities. Come back to check when you are ready. Okay, so 0.5 moles of magnesium. Well, if 2 makes 2, then 0.5 would form 0.5. Now, 0.5 moles of oxygen, we have to bear in mind that 1 mole of oxygen forms 2 moles of magnesium oxide. So 0.5 moles of oxygen would form twice that amount, 1 mole of magnesium oxide. 1 to 2, 0.5 to 1. It's the same ratio. This is a whole number ratio. This is the actual starting quantity of oxygen. So 0.5 forms 1 mole. It's 1 to 2. So apply it to 4. We're going to double 0.125, so that becomes 0.25 moles of magnesium oxide. So the ratio 2 to 1 to 2 is fixed, regardless of the starting quantities. So let's move on to calculating some reacting masses. So let's start with a different equation. 2 calciums, 1 oxygen forms 2 calcium oxide. So the mole ratio is 2 to 1 to 2. Predict how many moles of calcium oxide will be formed from the complete reaction of. So on this occasion, we're starting with a mass of calcium, which would be the type of measurement that one would have, or the type of data produced from an experiment. So 4 grams of calcium, how many moles of calcium oxide will be formed? Well, the first step is to convert 4 grams of calcium into a numbers of moles. So 4 divided by 40. 40 is the relative formula mass of calcium. Calcium exists as atoms. We've got atoms here. So from the periodic table, calcium 40. 4 divided by 40, we have 0.1 moles of calcium. 4 grams is 0.1 moles of calcium. The reacting ratio is 2 to 2, so that would form 0.1 moles of calcium oxide. Stop the lesson. Can you calculate the moles of calcium oxide formed in problem 2 and 3? Come back to check and correct when you are ready. Okay, so assuming you've done the calculation, turn 0.5 grams of calcium into a number of moles, 0.125. That would form, it's a 2 to 2 ratio, so 0.125 would form 0.125 moles of calcium oxide. The third problem, we got a different reacting ratio. It's a 1 to 2 ratio. So 0.16 grams is 0.005 moles of oxygen. We've divided by 32. 2 times 16 is 32. So 0.005 moles of oxygen. Well, how many moles of calcium oxide would that form? Well, it's a ratio of 1 to 2. So that would form twice as many, 0.01. 0.005 times 2 is 0.01 moles of calcium oxide. Now we can add an additional step to this calculation so that rather than calculating the moles of calcium oxide formed from an initial mass of calcium, we can calculate the mass of calcium oxide formed. So let's model it. 4 grams of calcium. First step, convert into a numbers of moles. We did that on the previous slide. Then predict the moles of calcium oxide formed. It's a 2 to 2 ratio, so 0.1 will form 0.1. But we can then convert that numbers of moles into a mass. So 0.1 is the numbers of moles times 56, the relative formula mass. So if you're not sure of that, look back at the slide 2 or 3 back. 0.1 numbers of moles times the relative formula mass of 56. 56 comes from 40 for calcium in the periodic table and 16 for oxygen. So 56 for calcium oxide. So 0.1 times 56 is 5.6 grams. Convert, 3-step process, convert the mass into numbers of moles. Predict using the mole reacting mole ratio. Convert the predicted numbers of moles into a mass by multiplying by the relative formula mass. 2 problems, 2 and 3. Stop the lesson, complete those calculations, come back to check when you are ready. Okay, so I'm going to reveal. I'm going to convert 0.5 grams into a numbers of moles by dividing by 40. And then I predict using the reacting mole ratio, 0.125 moles of calcium oxide. And then I achieve the mass of calcium oxide by multiplying the numbers of moles times the relative formula mass. 56 comes to 0.7 grams. I hope you got that. If you didn't, try number 3 again. Otherwise, I'm going to reveal now. Turn the mass into a numbers of moles. Predict using the reacting mole ratio. The reacting mole ratio is 1 to 2. So 0.005 would make twice that amount, 0.01 moles of calcium oxide, multiplied by the relative formula mass, gives us 0.56 grams as the mass of the product. So here are a couple of problems with a slight variation. Instead of calculating the mass of the product formed, can you calculate the mass of calcium required to form 1.12 grams of calcium oxide? So we know the mass of calcium oxide. What would be the required mass of calcium? So similarly, here's the required mass of product calcium oxide, 0.5 grams. What would be the required mass of oxygen to form that calcium oxide mass? So stop the lesson, see if you can carry out the calculation, come back to check and correct when you are ready. Okay, so to reveal the first one, I'm going to turn 1.12 grams of calcium oxide into a numbers of moles by dividing by 56, just to be absolutely clear. 1.12 divided by 56 will give me 0.02 moles of calcium oxide. It's a 2-to-2 ratio. So if my product amount is 0.2 moles, then I require 0.02 moles of calcium. So what's the mass of 0.02 moles of calcium multiplied by the relative formula mass? So required moles of calcium times 40 comes to 0.8 grams of calcium. So 1.12 grams of calcium oxide requires 0.8 grams of calcium. Here we're forming 0.5 grams of calcium oxide. So the mass of oxygen required, again, we now know the mass of product. What would be the mass of the reactant? So convert the mass of product into a numbers of moles by dividing by 56, as on the problem number 1. Then we have half the numbers of moles as we have of calcium oxide. So the moles of oxygen would be 0.0893. That's the moles of calcium oxide times 1/2. It's 2-to-1, which gives us the moles of calcium. Beg your pardon, the moles of oxygen. Multiply the moles of oxygen by the formula mass of oxygen, 32, gives us the mass of oxygen required to make 0.5 grams of calcium oxide. So the last couple of slides, using moles to produce balanced equations, quite particular to the AQA specification. Our knowledge of balanced chemical equations is actually derived from experiments where mass data gave us the number of reacting moles, in other words, the reacting mole ratios. So, an example. From experiment, a reaction between sodium hydroxide, sulfuric acid or hydrogen sulfate gives us sodium sulfate and water. The first step is to obtain reacting masses from experimental data. So the reacting masses were found to be 40 grams of sodium hydroxide, 49 grams of hydrogen sulfate, produced 71 grams of sodium sulfate and 18 grams of water. We then convert those reacting masses into reacting moles. So 40 divided by 40, sodium is 23, oxygen 16, hydrogen 1. So 40 divided by 40 gives us 1 mole. Hydrogen sulfate, 2 times 1 for hydrogen, 32 for sulfur, and 4 times 16 comes to 98. So 49 divided by 98 gives us 0.5 moles of hydrogen sulfate. Similarly, 71 grams of sodium sulfate is 0.5 moles, and 18 grams is 1 mole of water. We then deduce the whole number ratio for the reacting moles. So 1 to 0.5 to 0.5 to 1. Multiply that through by 2 gives us 2 to 1 to 1 to 2. So that's the whole number reacting mole ratio. And then you put those numbers into the chemical equation. So 2, 1, 1, and 2. So our reacting mole ratio appears in the equation as the balancing numbers, which you may have been taught as coefficients, but the balancing numbers reflect the reacting mole ratio, a whole number mole ratio. So here's a problem. Use experimental data to calculate the balanced chemical reaction between zinc and oxygen to form zinc oxide. Our data is 6.5 grams of zinc reacts with 1.6 grams of oxygen to form 1.8 grams of zinc oxide. So 6.5 grams of zinc, 1.6 grams of oxygen gives us 8.1 grams of zinc oxide. From this starting point, can you calculate the reacting mole ratio and therefore produce the balanced chemical equation? Stop the lesson, carry out the process, come back to check when you are ready. Okay, so I'm going to go through step by step. Well, we've got the reacting masses, convert those into reacting moles. 6.5 divided by 65, 1.6 divided by 32, 8.1 divided by 81. So our reacting mole ratio, our reacting moles is 0.1 to 0.05 to 0.1, but we need a whole number ratio. So multiply through by 20 or divide by the smallest number, divide through by 0.05, so 0.05 becomes 1, 0.1 becomes 2, and 0.1 becomes 2. So my whole number ratio is 2 to 1 to 2, and then put those into the equation as the balancing numbers. There is the balanced chemical equation, derived from experimental data. This topic obviously needs practice. You'll find some straightforward problems in the textbook, but make sure you've got access to answers. Then move on to AQA past paper questions. You'll find them mostly in question paper 1. If you found this lesson helpful, please recommend it to a friend. Thanks very much.